Black holes, man. They're like
Yeah.
the ultimate cosmic mystery, right? I mean, they suck up everything, even light, like it's gone.
Yeah, they're pretty wild. And for a long time, we thought we had them figured out, at least the basics.
Right, like massive object, huge gravity, everything gets crushed into this point at the center, the singularity.
Exactly. Infinite density, physics goes out the window. But what if I told you that the singularity, that point of no return, might not be what we think it is?
Okay, now you've really got my attention. What are we talking about here?
So we got to talk about Roy Kerr. This guy, he's the one who first figured out that black holes actually spin.
Right, right. And most of them do, if not all.
Exactly. So Kerr, he's back, and he's got this new paper that's basically turning the whole black hole world upside down. He's questioning the singularity.
Wow. Okay, so the guy who wrote the book on spinning black holes is now saying, hold on, we might need to rethink this whole singularity thing.
Pretty much. He's suggesting that what's happening inside a black hole might be even weirder than we ever imagined, but maybe not a singularity.
Okay, I am so ready for this deep dive. Let's get into it.
Let's do it.
So singularities. I mean, the end of everything, right? Crushed down to nothing. How does that even work?
It's tough to wrap your head around. We're talking about taking something massive, like imagine a star bigger than our sun 1,000,000 times over.
I'm trying.
And you're squeezing it, all that matter, into a point so small it practically doesn't exist. That's a singularity.
And that's where our understanding of physics just, I don't know, falls apart.
Exactly. The equations we use, they just don't work at that kind of density, that infinite point.
Okay, so that's the traditional view, what everyone's been saying about black holes for decades. But Kerr, he's saying, hold up, not so fast.
Yeah, he's looking at it a little differently. It's kind of like, well, you know those old maps? They try to flatten the Earth.
Right, make it flat, but it's all distorted, right?
Yeah, Greenland's huge, everything's wonky. But the map isn't wrong. It's just a problem of trying to represent a curved surface on a flat sheet.
Okay, I'm seeing where you're going with this. Space-time, black holes, it's all curved.
Exactly. We use these things called affine parameters to measure distances in that warped space-time around a black hole.
So the ruler we're using is kind of warped too.
In a sense, yes. And the traditional black hole idea, it says if that affine parameter, that measurement, reaches a finite point, boom, singularity, end of the line.
But Kerr's saying, not so fast.
He's saying that finite affine parameter doesn't necessarily mean the light ray itself has hit a dead end. It might just be our measurement, our way of understanding distance that's breaking down, not the actual fabric of space-time.
So the light might keep going?
Yeah.
But where? So the light in the black hole, it keeps going. But where does it go if not to the singularity?
All right, so buckle up because this is where Kerr's theory gets really wild. We're talking about rotating black holes, right? Which, as we said, most of them are.
Right, spinning away.
Okay, so Kerr found that in these spinning black holes, the light, it can actually get trapped. Not just trapped, but it gets caught in this kind of, I don't know, infinite loop.
Hold on, infinite loop.
Yeah.
Inside a black hole.
Yeah, it's like, imagine a moth, right? It's drawn to a light, but instead of hitting the light, it gets caught in this spiral, gets closer and closer, but never actually hits it.
Okay, I'm trying to picture this. So the light's forever falling inward, but never, like, reaches a bottom.
Exactly. And this isn't just some, mathematical quirk. This is coming straight from Einstein's equations, from the math that describes how space-time itself works.
Wow, okay, so if it's not a singularity, what is it then? At the heart of a black hole, I mean.
Well, Kerr thinks it could be something equally mind-blowing, but maybe a little less, paradoxical.
Huh.
He's suggesting it could be a super dense, rapidly rotating neutron star.
A neutron star. Wait, but those are already unbelievably dense, right?
Oh yeah, they're like giant atomic nuclei. But picture this. One spinning almost at the speed of light.
Okay, that's intense.
Kerr's saying that spin, that crazy rotation, it could actually be enough to push back against the gravity of the black hole.
So instead of collapsing into a singularity, it's like this balancing act.
Exactly. Gravity's pulling in, that centrifugal force is pushing out, and you've got this incredibly dense, super spinning object right in the middle. And this spinning neutron star, it might actually explain some of the weird things we see black holes do, like those huge jets of energy they shoot out.
So instead of a dead end, it's more like a cosmic engine.
That's a great way to put it. What Kerr's doing is opening up a whole new way to think about these things.
This has been amazing. We started with singularities, talked about light getting trapped in an infinite loop, and now we've got spinning neutron stars at the heart of black holes. It's like the more we learn, the weirder it gets.
It really is, but that's what makes it so fascinating.
Right. Absolutely.
A huge thank you to our expert for taking us on this incredible journey. And to our listeners, we hope you enjoyed this deep dive as much as we did. Keep those questions coming, and we'll see you next time.